9.0 magnitude earthquake that triggered a tsunami which hit the northeast of Japan on March 11, 2011 had caused large casualty, uncountable losses and massive destruction. While the Japanese government and the world are helping the survivors, they are also struggling to cope with another critical situation that had raised fear and uncertainty to the people in Japan as well as many other countries, and that is the release of radiation from several damaged nuclear power plant units in Fukushima. A few weeks ago we had an interview with a nuclear engineer on this matter, and today we are going to bring you additional information on this. And the person who is going to answer our questions is Dr. Carl Gibbons. Hello, sir.
Hello, pleased to meet you again, sir.
Nice to see you again. Before we get into the heart of the matter, could you give us a brief background of your profession?
Yes, I've had over 40 years in the nuclear industry. I was trained originally by the Atomic Energy Authority, UK Atomic Energy Authority, and joined as a graduate engineer. And I've had several engineering positions and in project engineering, project management, and then in senior management positions with the Atomic Energy Authority. I've been decommissioning site manager. I've also been involved with AA technology at Chernobyl, and also in later years with NATO in Ukraine, and also recently, over a decade, with nuclear fusion, and as assistant chief engineer at JET in Oxfordshire. And now I'm involved in nuclear safety on several safety projects throughout the United Kingdom.
Okay, last time we gave a short description about how a nuclear power plant works or how it functions, but for those who may have missed the program, could you go through it briefly one more time about how a nuclear power plant functions and especially what happened to the one in Fukushima?
Yeah, basically a nuclear power plant isn't any different than any other power plant. It's only the fuel and the source of heat which differs. In a nuclear power plant you have fission which creates the heat, and the heat is extracted in several ways depending on the design of the nuclear power plant. In Japan at Fukushima, the power plant there is a boiling water reactor where the water that's taken, that's in contact directly with the nuclear fuel, in itself is used to generate steam and goes through turbines. In the United Kingdom we have one pressurized water reactor which is different. The water that's in contact with the fuel is actually used to heat a secondary cooling system which isn't in contact with the nuclear fuel, and that is used for a steam power plant. At Fukushima on the 11th of March there was an earthquake, but what was more dangerous for the operation of the nuclear power plant was the tsunami that came after and was the cause of the problems to date. Firstly, there was an explosion in Unit 1, and what's happened initially because of the high decay heat. And I know the viewers will know that immediately the safety system cuts in when an incident, major incident such as a major earthquake, and shuts the reactor down by lowering control rods into the reactor. This stops any nuclear fission taking place, but because of decay heat that's already in the fuel, and this is as the radioactive, newly formed radioactive fission products decay, this is extremely high. Initially it's about 6.5% of the total load of the reactor. And a lot of heat is generating there. It's producing steam that's in contact still with the fuel. This would react with the cladding of the fuel, which is zirconium cladding, which would oxidize, but removing the oxygen from the steam produces hydrogen. I think that what has happened on the aftershock, this has allowed hydrogen to escape into the building, causing an explosion. On the second reactor, it's different, although they had an explosion, in that they decided to vent off the steam in the unit 2. This went into a suppression pool, which is outside the main containment of the nuclear reactor, and this again exploded, causing an explosion. And reactor 3 was a similar explosion to unit 1. Now reactor 4 wasn't operational, the fuel had been removed, and that fuel was in the cooling pond, or the cooling pool, which was filled with water. Again, because of decay heat and the fact that they weren't able to replenish water in the cooling pool where the fuel was stored, that evaporated, and again then, because these fuel pools are open to the atmosphere, and because of a lack of water, then the radioactive materials can then become mobile, and because they're not contained, they're extremely dangerous. And what made reactor 3 more dangerous than any of them is the fact that they had in them a different type of fuel, and this is using plutonium instead of uranium-235.
The last time we had an interview, it was about 1 week after the accident, and at that time you had rated it at level 4 on the International Nuclear Events Scale, or INES at the time. Mm-hmm. Where do you think it is right now, and what does it mean?
When we first spoke about this, level 4 was rated by the Japanese government. It wasn't. It was the Japanese government that rated that. Then it quickly moved to a level 5, and it's staying at level 5 at the moment. Looking at the INES slide, we see it goes from 1 to 7. The first 3 are incidents, which I won't bother going on at the moment, but more important is what happened at Fukushima was at level 4, which is a minor release of radioactive material unlikely to result in implementation of planned countermeasures other than local food controls. Now the next one that it jumped to was level 5, and that was quite quickly, and more important that this is concerned with deaths as well, because it says that level 5 is a limited release of radioactive material likely to require implementation of some planned countermeasures and several deaths from radiation. So deaths were or are expected at level 5. Now 6 and 7 also is concerned with fatalities, but in addition to that, a level 6 is a significant release of radioactive material likely to require implementation of planned countermeasures. And level 7, which was the Chernobyl disaster, was a level 7, is a major release of radioactive material with widespread health and environmental effects requiring implementation of planned and extended countermeasures. But at Fukushima, I thought at one time we were moving to a level 6. At this moment in time, it's still level 5, but there could be instances such as another major release that moves on to a level 6. But let's hope it doesn't go that far. Let's hope.
The most worry that people have right now are radiation and contamination. Mm-hmm. So first of all, explain to us the several types of radiation and the levels of danger.
If we look at the slide on radiation, if you look at the top, basically there's 3 types that are shown in this diagram. The top one shows quite a heavy particle. It's an alpha particle. It's about the size of a helium nucleus, and is stopped by a piece of paper. The next one is a beta particle, which is in the middle. Now that is more penetrative, It is the size of an electron, roughly. Will go through the paper, but will be stopped by aluminium foil, for example. Next you have gamma radiation, which is very penetrative. It's so much so that it's used on radiography of materials, of steels, and also is more penetrative than X-rays. Now you need a substantial amount of lead in order to stop the gamma rays, and in reactors they use gamma shielding, they use cement for and concrete for gamma shielding. These are extremely thick, and biological shields are very thick constructions. But there is another one not shown on this, which is the neutron, which will radiate. Now all this radiation is, there are many forms of radiation, and this is ionizing radiation because of the effect it has on the atoms within the body. And these particles or rays will strip the electrons from the atom and alter the construction of the cells within our bodies. Neutrons will also strip, as they pass through the body, they'll strip the electrons, and in addition to that they will collide with atoms in the body, and also as they split some of the atoms building the cells, they in turn will cause radiation and have beta and alpha particles, which again will produce a lot of damage through radiation.
Then of course with radiation comes the question of contamination. 2-3 weeks ago it was not expected that, or should I say not confirmed, that the radiation was going to spread far and wide, and it was expected to be contained. But we know that the situation is very different now. We know also that the radioactive materials are found in food products within Japan and other countries. So what is the real situation now, and how much should we be worried?
If we take ourselves back to the first program, one of the questions you asked me is about other countries, Thailand, how far it would spread. I did then and do now feel that it's not going to seriously affect other countries outside of Japan. But in the immediate area, you're always going to have a spread of contamination. My main worries were plutonium, because plutonium builds up in your body, and this is something which I'll explain just a little bit later on. But the zone will always widen. It will always spread away from where it should be, and it doesn't just stop there, because it becomes mobile. Once it's released, it becomes mobile, and this is why it's so important to get to a situation where you immobilize all the radioactive material. It's like at the moment, Japan made a statement that they've found the leak. No, they haven't found the leak. They found where the leak is seeping out into the sea. So containment is essential to stop the spread of contamination. I don't think people outside of Japan need to be worried. And obviously it's going to affect Japan as far as sending foodstuff to other parts of the world, because no one's going to take it. So it's going to affect their economy that way. But there is certainly special controls now looking at which food sources are being contaminated. As soon as it's found, I'm sure the Japanese government are stopping it. But I don't think we need to worry too much about it. But in Japan, it depends where their food source is coming from. Some leaks out naturally, because I'm talking about the food stuff can find places it shouldn't be going. But I'm sure the Japanese have control measures to make sure that doesn't happen.
Well, talking about that, another question comes to my mind is that would it be possible that maybe there are countries that would still import food products from Japan, if not for human consumption, then maybe for animals?
I would think that the Japanese have got very strict controls about that. So I do not think that Japan knowingly would do that. No, I don't think they'd do that.
But it's possible that it's going to reach or leak out without knowing.
I think if people have to be aware if they're buying foods from unknown sources, which I'm not saying couldn't happen. I think it's better to go and buy something branded, so you have some assurance. It's where you have unbranded food products, and which may have come from some dubious means, then you have to be careful. I'd say caution.
You mentioned about fusion a while ago, and it seems to be less of a danger type of energy producing. Could you tell us the difference between fission and fusion?
Yeah, sure. Fission is breaking up of the atom, and I think we showed a model in the first interview. Fusion is bringing together two lighter atoms, and in the case of where I was at JET, the materials were isotopes of hydrogen, deuterium, which is non-radioactive, and tritium, which is radioactive. So if we look at the slide, there on the top left-hand corner, we have a deuterium atom, which has, same as hydrogen, but one additional neutron. Non-radioactive, it's natural in the sea, it's a natural substance. Then the bottom left, we have tritium, which has one proton, and the proton defines it as hydrogen, and two neutrons. Now that is radioactive, but it emits a low energy beta radiation. And when those two come together, we have at the top, you can see a neutron coming out of the reaction, and at the bottom is the ash from a fusion reaction. That ash is non-radioactive. So if you look at the fission reaction, where you have a lot of fission products which are highly radioactive, the ash from a fusion reaction is non-radioactive. The neutron that you see flying off at the top to the right in a working reactor would go to a lithium blanket, and the action of the neutron hitting the outside layer, the lithium layer, would in turn generate more tritium fuel to be used later in a new fusion reaction. And the heat will be taken from the outside jacket and used to produce power from a steam plant. So it's basically a nuclear process to produce power which doesn't produce any radioactive material. The only radioactive material it produces at the end of the day is when the reactor is decommissioned. The reactor itself is radioactive because of the neutrons, because when it hits steel, it produces radioactive materials. But it's less hazardous to dispose of, and constantly over the operation of the reactor, you have no radioactive waste.
Well, then I'm sure people in general would welcome this form of cleaner energy. But speaking of which, why are many other alternative ways to produce required energy not as popular, like solar power, biomass, geothermal, oceanic sources? And why are some countries pro wind power and some not?
First of all, it's the availability of energy. There are two issues there. Is that type of energy available? If you look at Great Britain, for example, we don't have a lot of sun, plenty of waves, plenty of wind. So wind and wave power are two potentials for alternative energy. And I look at nuclear as being alternative, not the absolute, but another alternative. The cost of generating power as well is important. But I think more important to a nation is the security of their energy supplies. If you're buying energy, the country you're buying from you can have unstable prices. You can also have a position where they can cut off your supply. Now, once energy is cut off to your country, You have problems. You have problems with industry, and I think people these days have become too used to it, switch on, switch off energy. So they can flick the switch and switch on. It isn't possible with some of the alternative forms of energy because it doesn't blow wind every day. It doesn't sunshine every day. Geothermal's there, but geothermal creates some form of disturbance to the environment. So nothing is free. There are other alternatives which I think should be considered immediately, which is saving power. You know, proper insulation. Switch it off when you don't need it. I think these are far more important. They can make cost savings, and also it helps the environment.
How do you see the future of nuclear industry?
I see now there's a big upset, and people are going to want to look closer at alternatives to nuclear. And people are naturally frightened of things like radiation because you can't see radiation, you can't feel it, you can't taste it. And that's always been the case. But in the future, I think nuclear should be considered by most countries, but the safe operation of nuclear power plants and some form of control other than somebody needing to keep these operational because of financial benefit to themselves. There should also be proper control, and more openness, I think, with the public is important to get them on board, to get them feeling as if they're important in the decisions about such things as nuclear power.
So that's a part of the questions that we don't have time for. I have many more questions like nuclear waste management and safety measures, not just for the systems and plants, but also for the operators, especially after an accident like this. What should they do? But unfortunately, that's all the time we have for this time. If you have questions and comments, you can write to sue@patiamail-tv.com, and I will be happy to forward these comments and questions on to Dr. Gibbons. Thank you very much.
Thank you very much. Thank you.